Alrighty, so I'm going to get started. Today's announcements. As a reminder, the exam regrades are due noon on Wednesday next week. If you missed lecture last time and didn't check the lecture capture yet, the way to handle that is just staple a piece of paper on the front saying what you want looked at and why. Keep it brief but detailed enough that I can tell what your argument is, I guess, on getting points back. And make sure you check it against the key first, just to be on the safe side. And then, or come to me or your TA and ask, like, does this merit points back? Might save you some effort if it turns out not. And then get it to me either in person or my mailbox by Wednesday noon next week. And then once the deadline closes, I'll go through and figure out how I want to regrade things. Okay, so Chapter 16 sapling, I'm going to edit the due date, so that's due 9 a.m. next Wednesday. And Chapter 17, I should be opening either today or sometime over the weekend, because that's the chapter that I'm going to get started on today. And I posted the lecture notes for that either Wednesday or Thursday, a couple days ago. So I guess any questions about those before we get straight into it? Alrighty, cool. So, Chapter 17 is all about first off the allylic position, which we saw a little bit of in the dienes chapter, but now we're going to get more heavily into it, and also something that's similar but a little bit different, and that is benzylic reactivity. Okay, so this whole chapter is about taking mostly reactions that we've already seen or slight variations on them and looking at what happens when we do them at positions one away from an aromatic ring or one away from a double bond. So as a reminder, this is the benzylic group. It's an aromatic ring with an extra carbon in there. So this is like benzyl bromide, for example. So this here is the benzylic position. And we already know that this one we would call allyl bromide. It's a double bond with an extra carbon before it attaches to whatever else the rest of the molecule is. So this here, this carbon, one away from the double bond, is the allylic position. Okay, so we already saw a little bit of this in Chapter 15, but now we're going to get quite a bit more into the details on it. Turns out that, I guess we already know that for the allylic position, anything you can do that puts a charge or a radical at the allylic position is going to be way more stable than it would be if it not for the double bond. So charges and partial charges and radicals are much more stable at these positions. Okay, so just as a quick review of allylic resonance forms, if you do, say, like a positive charge here, you can hop that over, get a positive charge there instead. So always keep an eye out for that 3-atom cluster, or 2 atoms have the double bond, 1 atom has a charge or radical or whatever, and then you can flip which end is which and do resonance that way. So you can do that with a positive charge. You can do that with a negative charge. The arrow pushing looks different, but the end result is pretty much the same deal. So like that. Or you can do it with radicals. Again, arrow pushing looks a little different because here you've just got one electron and you have to get the other out of the pi bond. But same overall change. Okay, so we've seen that like in at least a couple different places so far. We saw it in chapter 15, and we also saw it way back in OChem 1 at a couple points. So that's the allylic position. We've got, just by virtue of having the double bond, at least 2 different resonance forms here. For benzylic position, it's even better. So I guess questions about any of these 3 so far? All right, cool. So benzylic, you automatically are going to get 4 possible resonance forms at least, possibly more if you've got extra groups on the ring. So okay, I'm going to swap chalk. This one kind of sucks. Okay. So let's try this with a carbocation. Pretty much for all of these, it's actually going to be a little bit similar to what we did during EAS, where we've got a carbocation that we're bumping around the ring. You just always want to keep an eye out for that 3-atom grouping, where you can do pretty much the same thing that we did for the benzylic form up here and swap which end is which. So this gets us to here. Now we look for another 3-atom group. That gets us to here. And now the next 3-atom group gets us to here. And if we wanted, we could like show arrows for this going back the way it came, or we could show like another arrow here and get us right back to the starting position where we have an aromatic ring. Let me draw that in actually. Okay, there we go. And get us right back to where we started with all 3 bonds inside the ring and a carbocation hanging out outside of it. Okay, so given that all else being equal, more resonance forms equals more stable, being in the benzylic position for any sort of charge is going to be even happier or even more stable than it was in the allylic position. Okay, so that one's a duplicate, just in case you want to sort of get back to where you started. Okay, so questions about any of that one? Yeah? Most stable using the benzylic form of the carbocation? Oh, you mean out of between these ones? Yeah. So I guess technically the first and the last one is the only one that has like the full set of pi bonds in the ring. So that's probably going to be the dominant form because that's shown as aromatic, but I think the other ones end up being like still reasonably significant contributors, especially since they're all secondary and this one's primary. But yeah, I guess like this one is probably going to be the major form. So, thanks. Okay. So then let's go through it for a carbanion, negative charge. It's pretty much the same set of resonance forms. So minus charge here, again, look for a 3-atom grouping. So like here. Puts us there. there. Or there. Okay, so again, same 4 possible locations for the charge. It's just the arrow pushing looks a little bit different, or quite different, because we're moving around an excess of electrons rather than a shortage of electrons. Okay, and then the third one that I have in here is radicals, which again puts the radical in the same places. It's just the arrow pushing is different. So you can put the radical there, or you can put it there. Or there. Or finally, there. Okay. So what does this mean in terms of useful applications? Basically, it means that any reaction we've done ever that involves putting any sort of charge or radical onto carbon is going to be way easier and faster if we do it at the allylic or benzylic position. Even if it's only a partial charge. Okay, so the majority of this chapter is actually going through a handful of reactions we've seen in the past, some from OChem 1, some more recently, and just seeing like, here's how it looks when you do it at the allylic or benzylic position. Doesn't this look way better than when we're just doing it on bare like alkyl carbons? How much faster is it? Okay, so a lot of this chapter is actually kind of a review, but it's sort of applying old reactions in a new context. Okay, so questions about that? Yeah. Yep, they do, which is why those ones are probably going to be the minor forms, but they are like significant enough that the charge is still way more stable, because I guess like aromaticity, there's a lot of energy at stake, but also, for instance, carbanions, there's quite a bit of energy at stake. Like those are very strong bases, and the more you can spread those electrons out across the molecule, the better things are going to be. So, Okay, so the first part of this, we're going to actually go through a lot of the alkyl halide chemistry from chapter 9, so like Sn1, Sn2, E1, E2, and look at if we do it to an alkyl halide that's attached at one of those positions, how much does it speed up the reaction? Okay. All right, so reactions with carbocations are first up. So hopefully you remember that out of the alkyl halide stuff we did, the 2 reactions that go through a straight up carbocation are going to be Sn1 and E1. So let's try both of these at the benzylic position and see what it gets us. So Sn1, if we're doing it benzylic, we can show our benzylic alkyl halide here. If you remember, Sn1 involves the alkyl halide dissociating first. which gets us a carbocation. And here's where we can show all of the other resonance forms that I drew out over here. I'm not going to do them again, though. And then whatever nucleophile we have can come in, attach to the carbocation, and give us the benzylic whatever nucleophile we stuck on there. Okay. Let me draw up E1 as well here, and then just to have the mechanism up, and then we can talk about how much things change by virtue of being at benzylic. Oh, sorry, yeah.
Is this stability of the resonance forms, does that allow Sn1 to happen even though the carbocation is primary?
It does, yep. Yeah, so even though like we covered, you know, primary doesn't form a carbocation, like as long as it's benzylic, like that's way, way more stable than even like a tertiary alkyl halide or tertiary alkyl carbocation. So yeah, this is a legit use of a primary carbocation. Yep. Mm-hmm.
Is that means that all the Sn1 and E1 reaction that we're going to do will be full possible outcomes?
So good question. Let me do E1 real quick for a point of comparison, and then I'll show like what actually stops that from happening. So, okay. Okay, so E1 at benzylic. For this, you actually need a second carbon coming off of the benzylic position, because if you're going to form a double bond, you're going to have something to form a double bond to, and obviously you can't form it into the aromatic ring if you want to keep aromaticity there. So, but the arrow pushing is pretty much the same. Alkyl halide drops off. Get a carbocation here. It's still benzylic, only this one happens to be secondary in benzylic. You know, not that it couldn't have been secondary up here too. I'm just drawing the simplest possible case for Sn1. And then again, you have access to all those nice stabilizing resonance forms. But to finish this one up, we're going to instead come in with a base, pull off an H, kick that down, and get a double bond there. So I guess in this case, you'd actually be making styrene, because the double bond is outside of the aromatic ring. Okay. So, okay, I don't think I explicitly drew this out in the notes. I just said it in like a sentence, but let me actually draw out why you only get the one product for benzylic. So say we tried doing it Sn1. So we've had the alkyl halide drop off. We get to this carbocation. I could have the nucleophile stick on here exactly as I showed up there, which would get me to the benzylic product. If I try doing a resonance form like this, got a carbocation here. That is a contributing resonance form. It may not be like the dominant one, but it is a resonance form. I could hypothetically show nucleophile coming along, sticking onto here. Giving me this. Why is this product not as good as the one that I originally drew up there? Yep, it's not aromatic anymore. So even though there's potentially 4 different products I could make, because the carbocation's in 4 different locations and the nucleophile could theoretically stick on 4 different places, it's only going to ever do the one as like the product that forms in any detectable amounts. Like none of these non-aromatic products get made just because they're nowhere near as stable as the one benzylic product. Yeah?
So that aromaticity is far more important
So I guess this kind of comes down to like a kinetic versus thermodynamic thing, but yeah, it turns out that I guess these are minor resonance forms, and also like the product is not as good. So I guess if you did like, how would that look? Okay, so maybe if you did like an energy diagram, you've got, yeah, sorry. Okay. Yeah, I was just trying to figure out how that would look. Yeah. But yeah, I think like in the long run,
So is that
yeah.
in the low temperature, low pressure
Mhm.
situation, the aromatic is more favorable. However, if there is a high temperature,
I guess the thing is like I don't think this one ever gets formed, so it may be just like maybe the temperature you would need to favor the kinetic product is just so low that at that point the reaction gets killed off entirely. But yeah, I think it ends up like either this is a minor enough resonance form that the nucleophile doesn't stick on, doesn't attach there, or I guess product stability ends up being the dominant factor. Maybe just the difference in energy between products is a lot bigger than the difference in energy between carbocations maybe. But yeah, to be honest, I'm not entirely sure like where the origin of that outcome is. I do know that you don't get this one though, so pretty much I'm trying to rationalize why that is, and it could be a couple different reasons, I guess. So, okay. So one other kind of consequence of having all these resonance forms is that if you have the ring with any groups attached to it other than the benzylic carbon that we're doing this reaction at, then the resonance forms actually start to look even more similar to what we're doing during EAS reactions. So I guess if other groups are attached to ring, then more resonance forms might be possible. All right, so this is actually going to follow exactly the same like activating versus deactivating rules for EAS because we're still looking at stabilizing a carbocation. So the same things that were good for a carbocation in the last chapter are going to be the same here. So for example, if the carbocation forms here, and then we can show the resonance forms. I'm actually going to skip one preemptively just so I can draw out one less form, but at some point we're going to get the positive charge down on that carbon. And then, you know, if we were just doing this on a bare ring, we would then hop it over to here and would be done with all the forms. But just like we did in the last chapter, if we ever get the positive charge onto an atom with a lone pair having thing, then the lone pairs can create one extra. Form here that's actually the most stable possible resonance form for this molecule because here everything's got a full octet. But if I had that OH group attached at the meta position, it wouldn't really help out so much because then I would never be able to kick in the OH group. So in other words, electron donating groups are going to help the reaction or speed up the reaction if they're ortho or para to the benzylic carbon. Conversely, electron withdrawing groups are going to hurt the reaction if they're ortho-para to the benzylic carbon. And then for both of these groups, if they happen to be meta, they're still going to affect the reaction rate just slightly, but it's nowhere near as much because then it's just up to induction or inductance rather than straight up resonance forms. So if we're ranking reaction rates, having a nitro group be ortho or para to where our carbocation is going to form is the slowest. And then just like in last chapter, having it meta, it still slows things down a bit, but not by as badly if it's ortho or para, which is why nitro groups during electrophilic aromatic substitution happen to be meta directing, because meta is the position that doesn't get messed with quite so badly. But better to have an electron donating group. Here it's slightly helping the reaction, just not very much. If we put it ortho or para, then it's helping the reaction out a ton. So this is fastest. Okay. So if you want, you can go through like all of these, show the carbocation forming, show all the resonance forms, and like rationalize to yourself like what's going on in terms of how good or bad is the effect that this thing has on the product or on the rate of the reaction. But it's really going to come down to pretty similar behavior to what we saw at the end of chapter 16. Okay. So questions about that? Okay, cool. So in general, I don't know if I explicitly said this yet, but in general, having an alkyl halide be at the benzylic position is usually several hundred times faster than it would be if it were just an alkyl halide. Okay, so this is all for the benzylic position so far. Allylic position is going to be kind of similar. It's sped up a bit, not by quite as much because it only has the one additional resonance form. But we already know from a couple chapters back that allylic we have to worry about one additional thing, which I guess we sort of got into here a little bit, which is we could get multiple possible products. So it's sped up compared to alkyl, but now we really do have to worry about are we going to get more than one thing out of this? So this isn't exactly the same as like 1,2 versus 1,4 addition, but it's got some similarities between them. So instead of having like a conjugated diene where we start this reaction, we could have maybe like an allylic halide or something, an allylic bromide here. And get a carbocation at the allylic position that way. And now we've got kind of like when we're halfway through 1,2 versus 1,4 addition, we have a choice to make because we can do resonance forms on this. And either one of these, say we're doing like Sn1 for example, either one of these could have the nucleophile stick on to that carbon. Okay, I think in the notes, I actually say that this bottom one is major. That I am going to have to go back and revise because that's not universally true. This comes down to like a kinetics versus thermodynamics thing again. So here, this one happens to be the best product, so that's thermo. This one happens to be the best intermediate because it's the most stable carbocation location. So that's kinetic. So yeah, in the notes I say it favors this one. I guess that would be only under kinetic control. If you heat it up long enough and give it its free choice of whichever product is the most stable, it'll pick the thermo one. Okay, questions about that? All right, cool. Alrighty, so the next thing that we're going to look at is sort of, it's a reaction that we've seen before, but we haven't applied it specifically in terms of resonance at these positions, and that is reactions with radicals. Okay, so if you guys remember radical halogenation of alkanes, where we, let me just do like an old example here. Okay, note that this is not an aromatic ring, this is just like an alkyl halide of some kind, and I'm drawing it that way so that we have a tertiary proton on there. If we do Br2 and UV light, written as H nu, we are going to, at least in the past when we covered this, what we did was rip off the proton at the most substituted carbon and then replace it with a Br. And if you remember, we could do this reaction with chlorine too, but chlorine is a lot less picky, and that unfortunately gives us a mishmash of different products. So we might get chlorine stuck on like here or anywhere around the ring. So generally, bromine is kind of the way to go for this if we want selectivity. Okay, so when we were doing this before, we always did the most substituted hydrogen, but really, the determining factor is we want to make the most stable radical at that location during the reaction. And if alkyl is the only thing that you have in the molecule, then most substituted happens to also be most stable radical. So, given what we now know about resonance forms and radical stability, we should expect that things might be a little bit different now that we're bringing in benzylic stuff. So here's sort of a interesting example. So here's a molecule that has a tertiary carbon in it. Note that I do not have an H here. That's kind of a place where people trip up. Remember that if it's an aromatic ring, then each carbon has only one bond to stuff outside the ring. Okay, so Br2 and H nu on this. If we're following the old rules, we'd expect our bromine to get attached out here. It's the only tertiary proton in the molecule that can get replaced. But we're actually going to halogenate it only at the benzylic position preferentially. Okay, so in other words, the reaction is faster at benzylic than at just tertiary alkyl. And that just comes down to resonance. Okay, so I'm not going to go through the entire mechanism for this one. That might be, if you're feeling a little shaky on it, it might be something worth reviewing. but at some point you get a radical on this carbon, and then you can show it moving around the ring through resonance, kind of like I did on the first third of the board over there. Okay, so benzylic, pretty simple. If you've got any benzylic H's, those will be the first to go. Allylic, kind of like we saw in this case, it's a little bit messier because we can get multiple products, and also there's something else to worry about. Okay, so allylic, say we're doing it on the cyclohexene, Br2 and H nu. So again, it's going to preferentially halogenate the allylic position, again, due to resonance stability. But there's a big complication here. Say that while we're reacting these molecules, H nu happens not to get any of its photons involved in the molecule, or maybe there's not enough light or something going on. In that case, what reaction does this look like from OChem1? Yep. So, whoops, that's not what we were going for. Okay, so in practice, we pretty much can sort of pick and choose one over the other by limiting or maximizing the amount of light. So if you want to favor adding Br2 specifically to the allylic position, you want to blast this thing with UV. You can actually, like, I didn't cover this explicitly in my lecture, but it sounds like I think Professor Jin might have last semester. It turns out you can also force this to go by heat as well. So if you heat it up a ton, you can actually promote radical formation that way. Or just get like this giant UV lamp and shine it into the reaction. And you'll probably favorably make the radical addition. If you want to do this one, a lot of the times they'll actually say Br2 in the dark. So either you turn the lights off in the fume hood and put up like some cardboard boxes around the flask while you're doing the reaction, or you can actually just get some foil and wrap it around the flask, and that'll stop most of the light from getting in and favor the dihalogenation mechanism.
Why is the UV light can make it this high?
So really it comes down to so BRBR, or CLCl if you're doing it that way, has some tendency to like do a homolytic cleavage like this, where it splits into two radicals. And as soon as that happens, it's going to go off and do this radical addition mechanism. But if you can minimize how much it wants to break up like this, then it's going to stay BRBR, and then that'll let you get into this like it stays together, and then the double bond gets involved. That's kind of a crappy way to draw with a halonium ring, but yeah, that's kind of where we're going for here. So it's basically like, is the bromine by itself as a radical when it encounters the ring, or is it still with its other bromine when it encounters the ring, and that's going to change like how they react with each other?
So if that means that by using the photon, shooting the bond between the BRBR, it actually can cause a radical effect.
Exactly, yeah. Yeah, so it's just down to like radical generation rates versus rates of reaction. Yeah, so it's very likely that even though we like have been doing this reaction in OChem1 and we're like, oh yeah, just an alkene plus Br2, you'll get the diradical addition product. Turns out there's more going on than that. Pretty much any excuse for bromine to split into radicals, and you'll probably be getting this going on as well. So, welcome. Okay, so other questions about that one? Okay, cool. So there is actually another way to favor radical addition. And that's by using a new reagent that we haven't covered yet. Okay, I still got 5 minutes. So I guess radical addition over dihalogenation is what we're trying to maximize. I mean, if we're trying to maximize that. So this reagent is called NBS, and that's usually how it's written on the arrow. And that stands for N-bromosuccinimide. There's also the less popular versions of NCS and NIS. For chlorine and iodine. Oops. But NBS is by far the most commonly used. So what this looks like is, and you don't need to know the structure of this, but just in case you're curious. Okay. So it's this aromatic ring with a couple of carbonyls coming off of it, both of them attached to a nitrogen, and then that nitrogen has a bromine coming off of it. So this whole part is succinimide, and then we've got a bromine attached to the N, which is why it's named the way it is. Turns out that this thing is actually quite good at stabilizing radicals on both halves, so kind of similar to how BR was good at forming two radicals. This thing can actually split off into two radicals. There's a little bit of, I guess depending on which source you ask, sometimes if you sort of leave this to sit around by itself, the bromines will actually get together and generate small amounts of BR, like dibromine, which will then, like, there's enough light around to have that split into radicals and do the reaction. Or some sources show this just going straight in for the radical addition, or radical proton abstraction, hydrogen abstraction. Okay, that's actually an important distinction. We're not pulling a proton off of this molecule because it's coming with one electron. It's actually got, we're extracting a hydrogen, not a proton here. And I did not draw that correctly. Okay, so that's going to be pulling the H off of the molecule. And then you can either show BR radical attaching on there, or you can show this doing a propagation step where it, using its radical electron, pulls the BR off another NBS molecule. So technically this would be a termination step. So whether this goes by a chain reaction or it like terminates each time, I think kind of depends on concentration and like how much light there is around and how fast you're making radicals and some other things. So I'm not going to get like too bogged down in the details of the mechanism, but this is a way to show it. Okay. So questions about that one? Okay, cool. Real quick, if you're the person that emailed me about picking your exam up from your TA and you can't make it next week, I have your exam here with me right now, so come grab it. Otherwise, I'll see you guys on Monday.